Matrix multiplication today. So we saw that, we played around with it on our calculators on Thursday and came up with a weird rule, which you have probably since forgotten completely. So we will look at that again and remove it. Now, adding and subtracting was super easy because it was very intuitive. You can only add if you have the same size of matrices, and you can only, and then you only have to add the corresponding spots. For multiplication, they don't have to be the same size, but they have to be compatible. And to be compatible, when you put the dimensions side by side, the middle numbers have to match up. So in other words, you've got your columns of your first matrix have to match up with the rows of your second matrix. And then when you multiply them, your answer the size of your answer will always be the outside number. So it's kind of interesting that way. So in order to be compatible, those middle numbers have to match up. If those middle numbers don't match up, they won't be able to be multiplied together. So again, here is the same idea. These numbers have to be the same. And there is the size of your answer. So the way that it works, first we're going to check the dimensions. And we remember that matrices rock, rows first, columns second. So here we have 3 rows by 2 columns. Here we have 2 rows by 1 column, and our middle numbers are equal. So we will be able to multiply these. This one's not possible because this is a 2 by 2, and this is a 1 by 3. And the middle numbers do not match up. So, first you establish if you can multiply them. Once you've established if you can multiply them, then you know the size of your answer. So for example, this one again, this is our 3 by 2 multiplied by our 2 by 1. Our middle numbers match, and the answer is a 3 by 1 based on those outside numbers. So at least you can set things up so that you know how many answers you have to get. And then to get each element in your answer, you have to multiply a row by a column. And each the row gets turned on its side, and each corresponding element multiplies with each corresponding element, and you add them up. So this is what it looks like. So first of all, I'm going to do some color coding here. We know that the answer was going to have these 3 answers in the end. Okay? And initially, you wouldn't know it was going to be a 23, 53, and 83. You would just know I'm multiplying these together. My final size is a 3 by 1, so I have 3 answers to get. To get the blue answer, okay? That blue answer is in row 1, column 1 of your answer. So it's going to come from row 1 and column 1. So if I circle those in blue, and again, I take the row, I turn it on its side, I ram it into the column, The 1 would hit the 7, the 2 would hit the 8. And you would get 1 times 7 plus 2 times 8 and get 23. Color coding our second one. Okay? Here, this is in row 2, column 1. So we take row 2 and we take column 1 again. Again, I like to imagine taking that row, turning it on its side, ramming it into the column. 3 hits a 7, that's 21. 4 hits a 8, that's 32. Add them together, and you'll get 53. And finally, the purple one, its position in the answer is row 3, column 1. So now we would take row 3, turn it, multiply the corresponding elements, add them together, and get 83. So here are some examples. First of all, you need to know how big your answer is and whether they can multiply. So here we have 2 matrices. The middle numbers are the same. So the answer would be a 1 by 2. And of course, you could not multiply those in that order. But if you switch the order, you could. So this is something in mathematics I don't think you've run into very much before. Your whole life in multiplication, you've been told the order doesn't matter, right? What's 5 times 7? 35. What's 7 times 5? 35, right? It doesn't matter the order. If you know one, you know the other. But in matrices, it does matter the order. Sometimes, like in this example, one way it works, one way it doesn't. And in other examples, if it works in both directions, sometimes the answers are different. Well, most of the time the answers are different when you multiply them. Okay, so let's do some mental math. Here are 6 to try without, without a calculator. See how you did. There's C times A. There's A squared. And there's one that was hard to click was not possible. So, is the math hard? No. Is it easy to make a mistake? Yes. Okay, so I think that sometimes puts it up on the frustrating list because it's not hard, but it isn't easy to make a mistake as you're going along. But we just have to be careful. And you have your calculators. If you have a graphing calculator, you can put these in and you can check them to see if it's working or not. So here's a new word for you. Commutative is the official word for when 5 times 3 is the same as 3 times 5. There's a fancy word for that. Most of us up till now have just thought of it as common sense. Okay? But there are words for this in mathematics, in formal definitions, and commutative means that you can multiply, doesn't matter the order. Matrices, that doesn't work, right? So we have the following laws of multiplication. Some of them follow laws that you already know for multiplication, and some of them don't. So the first one is one of the ones that doesn't. A times B is not the same as b times a. However, here's another new word for you, associative. If you're multiplying three things, you could choose to do the a times b first, or you could choose to do the b times c first, and it comes out to be the same number. So as far as when you're multiplying three things, which two you do first, that doesn't matter. You can distribute with matrices. So if you have two matrices added inside, and you're multiplying by a matrix A outside, you could distribute. Now, if we think about it, how easy was it to add matrices? Super easy. So why would you choose to multiply twice instead? I don't know. Probably I would choose to add them, but, right? There's the fancy word for this, but this one you've heard, because this one we use since grade 9, the distributive property. So you've seen that word a lot more. There exists an identity, sort of like a number 1 for matrices, right? Multiplications table with 1 is so awesome. You guys are really good at it. You can even test notes. 5.32 times 1. 5.32. Feels so good about multiplying by 1. It exists in matrices as well. And when you're multiplying by 1, you can multiply it after or multiply it in front. It's still equal to what you started with. And there is an inverse. So that when you multiply by the inverse, you get 1. The inverse of a number is dividing, right? Like 5 divided by 5, you get 1. If you divide by itself, you get 1. There is no dividing in matrices, but there is inverses. So, for example, in matrices, 5 divided by 5 doesn't exist. But in matrices, 5 times 1/5 does exist. So we can multiply, but there is no matrix division. So these are some of the things that we're going to work at over the next little bit. Working with matrices, but before we do that, why is matrix multiplication the way that it is? We're going to find that out.